Okay, today we're going to learn about our fourth type of reaction. They're called double replacement reactions. Okay. So double replacement reactions. It involves the exchange of two cations between two different compounds. Okay. So one compound, a second compound, the cations are going to switch spots. Okay. So when I saw you Monday, I gave you the dancing analogy, right? Where like one could change dance partners. Okay. This time, think about like two couples dancing and like partners are just going to switch. So one partner changes to one couple, the other partner swaps over here. Does that make sense? Can you like picture that in your head? Okay. Two options though. Do you have to switch your dance partner if you want to or if you don't want to? Yeah. You don't have to, right? So sometimes you can mix these solutions and there's no reaction. Okay. Other times you can mix them and you get a chemical reaction. So just because we mix two chemicals together, it doesn't automatically mean that they'll react. So when we have double replacement, two options. So either a no reaction or a reaction. Okay, so on the previous slide we said sometimes a reaction will happen, other times a reaction won't happen. So when we do reactions in real life, what are we looking for that tells us a reaction actually happened? Okay, so one, you're looking to see if a gas is produced. When we do double replacement reactions, it's always two like liquid solutions. Okay, so if you mix two liquid solutions and they make a gas, what's that going to look like? What are you going to see that tells you a gas is being made? Bubbles. Okay. So if you want, by like gas being produced, you could also write bubbles. Sometimes when we mix the liquids, we get a solid. So if we take like liquid plus liquid and you make a solid, you definitely made a new product. We call that solid a precipitate. And then finally, for double replacement reactions, the reactants are always two ionic compounds. If your two ionic compounds combine and make a molecular compound like water, then that also means you made a new product or you had a chemical reaction. Okay, so molecular compound, and it's almost always going to be water, sometimes maybe carbon dioxide. Okay, so it'll be like a very common molecular compound that we're familiar with. Okay, so we talked about in real life, what are we looking for to know if a reaction's taking place? Well, we also have to know like on paper. How do we know if a reaction takes place on paper? So we're going to use solubility rules. Okay, so take the chart that you received on Monday. Take a look at the backside. Right, so everyone take a look at the solubility rules. So we use these rules to help us predict if a chemical reaction will actually occur or if no reaction will occur. Okay. If both of our products become soluble in water, then no reaction happens. If we produce any products that either make a molecular compound like water or we get something that's insoluble, then yes, a chemical reaction occurs. So I think the best way to learn how to do this is just to do a couple practice problems together. Okay, so I'm going to change the slide. We'll do some practice problems, and then we'll use this as we do the practice problems. Okay, so here's our first one. We're going to take sodium sulfide and add it with cadmium nitrate. So copy this down. Okay, so when we do double replacement reactions, first you just have to know, well, how do you identify that it's a double replacement reaction in the first place? Will I always be here to tell you the type of reaction it is? No. Okay, so what do you notice about, what are you starting with this time? What are both of these? Are they single elements? Okay, what are they? They're compounds. Okay. Notice we're starting with two compounds. Okay. So anytime you see two compounds as reactants, you should be thinking double replacement reactions. Then in the double replacement reaction, the cations switch places. So if we think of like the dancing analogy, the cations are going to swap their dancing partner. This is why I chose the warm-up today. Cations always come first. So that's sodium and cadmium. Okay. So when I say they switch places, cadmium is going to take the spot of sodium and it's going to bond to sulfur. And then sodium will take the spot of cadmium and it'll bond to nitrate. So when we write the products, every single time we have to do the charges and like the crisscross rule. Okay. So I'm just going to start with sodium since it's first. So sodium is going to take this spot. So what's sodium going to bond to? Nitrate. Okay. So we have to look up the charges. So what's the charge of sodium? Okay, +1. Nitrate is NO3. And where would you find the charge for nitrate?
The back of that right there.
Okay, you would find it on your naming chart. What is the charge of nitrate? Charge. Look at the charge. Okay, -1. So now that we have the charges, what do you do?
Crisscross.
Okay, crisscross
Do you have it on there? Like all the
most. What do you get for a formula? Good. NaNO3? Good. Okay. And then our second product, cadmium will take this spot. And what's cadmium going to bond to? Okay. Cadmium's going to bond to sulfur. Again, every single time you have to look up the charges and do the crisscross rule. Every single time for these. So cadmium, if you find it on the periodic table, it is number 48. So it's a transition metal. What's special about those charges? Okay, it's not like a one size fits all. Find cadmium on your naming chart though. What is the only charge listed? Nope, look again.
Wait, what is it?
What's the only charge listed for cadmium? Okay, so cadmium can only have a +2 charge. I'm making you look it up this way because this is simpler. If you wanted to, could you like reverse the crisscross rule over here and figure it out?
Yes.
Yeah.
You could. Is it easier just to look on here? Okay, so cadmium's +2. What is sulfur? Okay, -2. What do you get when you do the crisscross rule?
Nothing.
Okay, nothing. You get CD2S2, but can those 2's reduce? Okay, so you should get CDS.
Yep.
Okay,
What happens if you don't reduce it?
nothing major. It's going to affect balancing a little bit though. Okay, here's the new step. So now we have to figure out the solubilities of these products. So we're just going to start with sodium nitrate. Okay, so everyone look at your solubility rules. What's the first column? Like what's the title of the first column? Look above that. What's bolded? Negative ions. Okay, so when you use the solubility chart, it's typically easiest to find everything based off of the anion. So if we look at sodium nitrate, which one's the anion? Nitrate. Okay, the anion goes second. Okay, so find nitrate. So you're going to go down until you find nitrate. Which row is it in? Fourth row. Okay, then you go over to the cation. So nitrate, it's any cation. It doesn't matter what it bonds to. What's the solubility? Okay, soluble. What does it mean if something's soluble? It dissolves. So let me show you what that would look like. Okay, I'm going to change my color because I'm going kind of on a side note. So it's soluble. So that means when sodium nitrate is in solution, that bond breaks. So you get these little sodium ions floating around, and then you get these little nitrate ions floating around. Okay. So when those end up in solution, we call it an aqueous solution. Okay. So you're going to write AQ for aqueous. Everybody say aqueous.
Aqueous.
Okay. Okay, so even though it says like soluble on here, soluble translates to AQ for aqueous. All right, now we're going to do the same thing for the cadmium sulfide. Okay. We're going to start with the anion. What's the anion? Okay, sulfide. So on your chart, go down until you find sulfide. Okay, it's the bottom one, right? So then notice there's like two different rows. So take a look at the top row. Is cadmium part of those alkali ions or alkali earth metals? No. So you go one below where it says any other cation. Okay. And then what's the solubility? Okay. Low solubility, and then in parentheses it's insoluble. So that means it doesn't dissolve in water, meaning it'll make a solid. So you're going to put an S there because it makes a solid. We call that a precipitate. Okay. So since you made something new, did a chemical reaction happen? Yes. Okay, so like if we were to take these two chemicals and mix them, we would end up with an actual solid. Okay. So yes, a chemical reaction happened. So then yes, you have to balance it. And if we're going to balance, start with the most complicated. So nitrate is NO3. How many are there? 2. So what do we need to put right here? Okay, so I'm just going to put a 2 there. So that 2 distributes, so there's 2 nitrates. It also causes us to have 2 sodiums, and we already have 2 sodiums. 1 sulfur, 1 sulfur, 1 cadmium, 1 cadmium. Are we balanced? Good. All right, here's our second example. So we'll take NaCN plus H2SO4. So copy this down.
Did you already do a tangent?
Okay, before we even get started, how can you tell that this is a double replacement reaction?
It has 2 compounds.
Good. 2 compounds. Okay. So notice 2 compounds. That'll tell you that it's a double replacement. Okay. So then double replacements. The cations swap places. So sodium will take hydrogen's place and it'll bond to sulfate. Hydrogen will take sodium's place and bond to cyanide. So sodium is going to bond to the sulfate. We have to do charges every single time. So what's the charge of sodium? Okay, sodium's +1. What's the charge of sulfate? Good. Okay, -2. All right, so then what's your next step? Crisscross. What do you get? Good. Okay, so you should get Na2SO4. All right, then hydrogen takes sodium spot and it bonds to cyanide. Okay. So this is where you just have to be careful. Make sure you always write that cation first. So hydrogen goes first. Hydrogen gets a charge. It is in the first column. So what kind of charge do you think hydrogen will get? Okay, so it's going to get a +1. Cn is cyanide. It's one of those polyatomics, so where would you find the charge for cyanide? You would find it here. So if you look up cyanide, what's the charge? Okay, -1. So if you do the crisscross rule, what do you get? Nope. No. So take a look up here, Alex. It's just a +1
No, I was
charge.
talking about the
Oh.
hydrogen base.
Okay. Okay, so products. Every time you get your products, you have to do the crisscross rule. Okay. Next step is solubility. Okay, so get that solubility chart out. First one, sodium sulfate. Are we going to find it based off sodium or sulfate? Okay, sulfate. So you use the anion. Okay. So go down till you find sulfate.
Second left.
Okay, second to last one on the left side. You've had that top row. Is it bonded to any of those like ions listed?
No.
Nope. So you go down to the any other cation, and then what's its solubility?
Soluble.
Soluble. So what are you going to write?
AQ.
Okay, AQ. So soluble means it's going to dissolve, and it makes this aqueous solution.
I just think of it like water, like aquatic.
Good.
So-
Ooh, yeah, that's exactly right. Okay, next, let's look at HCN. CN is cyanide. Take a look at the table. Do you see cyanide anywhere? Okay, so cyanide isn't on this table. Do you agree?
Yeah.
Okay, so then you're going to have to use the cation. So now you're going to switch over to the cation column and go down till you find hydrogen. And it should be pretty close to the top, right? What row is hydrogen in?
Wait, where is Canada?
The middle column, like the second column? How many rows down is hydrogen?
Second.
Okay, second row. Does it matter what hydrogen is bonding to? Does it matter what's its solubility?
Soluble.
Okay, soluble, so what are you going to write?
AQ.
Okay, AQ. Okay, let me show you what this looks like. So I'm going to start on the left. Okay, so sodium cyanide is aqueous. So that means when we put it in solution, it breaks apart and you get these sodium ions and these cyanide ions. Okay. H2SO4 is aqueous. So you get hydrogen ions and sulfate ions. Sodium sulfate is aqueous. So you get sodium ions and sulfate ions. And then hydrogen cyanide is aqueous, so you get hydrogen ions and cyanide ions. Okay, so look up here in my red. Is there any difference on the left side of the arrow compared to the right side of the arrow?
No.
Okay, do you see where we have exactly the same thing on the left as we do the right?
Yes.
Okay, so did you make a new product?
No.
Did you have a chemical reaction? No. So when you see a situation like this, you can just write NR for no reaction. Okay. So if there's no reaction, do you have to balance it?
No.
No, don't worry about balancing it. You do need to get this step though. You have to show me the products and you have to show me they're both aqueous because that tells me that like you understand if they're both aqueous, it's no reaction. Okay. But I want you to like, does that make sense if we break it down into ions? You can see the left side and the right side, there's 0 changes. Okay, so if we were to actually mix those chemicals in real life, nothing would change. Okay, it would be exactly the same thing. We didn't make anything new. Okay, one more that we'll do together. We have calcium hydroxide plus hydrochloric acid. So go ahead and copy that down. Okay, so calcium and hydrogen are going to swap places. So if it's helpful, you can draw the line so you know which one's which. So calcium is going to bond to chloride. Okay. Can we just go CaCl and call it a day?
No, I wish.
I wish, but no. So we have to look up charges. What's the charge of calcium?
2.
Okay, +2. What's the charge of chloride? Okay. So when we crisscross, what do we get?
CaCl2.
Good. Okay, then hydrogen is going to bond to that hydroxide. What kind of charge does hydrogen get?
+1.
Okay, +1. Hydroxide is a polyatomic. If you look it up, what's the charge? -1. So if we do the crisscross rule, what do we get? Okay, HOH. Does HOH look familiar? How else could you write this formula?
H2O.
Okay, H2O. What is it?
Water.
Water. Okay.
That's what it looks like without it being bonded.
So
Like,
HOH is water. I would recommend you keep it as HOH, and I'm going to show you why. Okay. This one, water, it's not an ionic compound, so it doesn't have a solubility. However, at just like normal room temperature, what's the state of water? Like the physical state. It's just a liquid. Just a liquid. Okay, so if you get HOH, you're thinking it's water. Okay. You don't look up the solubility. It's L for liquid. Okay. So water, it's a liquid.
I was like thinking about orange juice. I thought of OJ, and I was like, hold on. And then I was like, wait, that's not.
No.
Anyways.
Okay, calcium chloride. Try to look up the solubility without me. So what is the solubility of calcium chloride? Soluble. What does that mean?
That it's AQ.
AQ. It means it's going to break up in water. It'll dissolve.
Which would just be chloride, right? Not calcium.
Well, you get like calcium ions and chloride ions. Okay. You made a liquid, so because it's not aqueous, yes, you have a chemical reaction. Okay. You made something new, so yes, chemical reaction. So do you have to balance?
Yes.
Yes, you have to balance. Let me show you a little trick I used. So when you have hydroxide, keep water as HOH, okay? And if it is helpful, I'm going to change my color so you can see what I'm doing. You can put parentheses around this OH, okay? So when you balance, you're going to keep OH together and OH together, and that's going to make balancing a lot easier, okay? And since that's our only polyatomic, we'll start there. So how many OHs are on the left side? 2.
2.
So what needs to go right here?
The 2.
Okay, so I'm going to put a 2 here. Okay, so this 2 distributes, so there's 2 OHs. And then now, how many hydrogens are there?
2.
2. So what do you have to put right here?
2.
2. Okay. So 2 hydrogens. Also, it distributes to the chlorine, so 2 chlorines. And how many chlorines are over here?
2.
2. There's 1 calcium and 1 calcium. So are we balanced?
Yes.
Good. Okay, so try this one on your own. See how far can you get without any help, and then I'm going to circulate, so if you need some help, call me over. Okay, let's check your work. So what's one of your products? BA, hold it. So,
BACO.
hold it. BA,
Oh, okay. Yes, so I was right.
it'll go CO3. So when you do the crisscross, what do you get?
BACO3.
Good. BaCO3. Okay. And then potassium bonds with chlorine. What's the charge of potassium? Plus. And what's the charge of chlorine? -1. Okay. When you crisscross, what do you get? Okay. KCl. Okay. What do you have to look up next? Solubility. What's the solubility of barium carbonate? What did you get? Insoluble. So that means you make a solid. So you're going to write an S for solid. And then what's the solubility for potassium chloride? Okay, soluble. So what are you going to write?
AQ.
Good. AQ. Okay. You made a solid, so did you have a chemical reaction? Yes. Okay, so do you have to balance?
Yes.
Okay. What do you have to add to balance?
2.
Yes. Where does the 2 go?
BA. No. No, it's already. Well, I don't know.
No, none for the BA.
Well, Haha.
If we put a 2 there, is it balanced? Okay, I just want to point out one special type of double replacement reaction is just an acid-base reaction. So if you mix an acid and a base, it's just a double replacement reaction. Your products are always going to be water and some sort of salt compound. Okay. So I did hydrochloric acid and sodium hydroxide. You'll always get HOH. What is HOH?
Water.
Always, always, always water. And then depending on what's left over, you'll always get some sort of salt. Okay. So just acid base is just a, I don't know, special type of double replacement where you always get salt in a water. So if you ever need to neutralize an acid or a base, what can you mix it with? The opposite, right? If you need to neutralize an acid, mix it with the base and you'll get salt water. Can you easily just dump salt water down your drain?
Yeah.
Good. Or if you had like a base at home and you need to get rid of it, can you neutralize it with some acid?
Yeah.
And then can you just dump it down the drain?
Maybe.
Yes.